Dark matter does not shine, does not speak, and does not touch you in any way you can feel. And yet, right now, it outweighs everything you have ever seen. Invisible to light, silent to every sense, dark matter makes up roughly 85% of all the matter in the universe. It threads through galaxies like an unseen skeleton, holding stars in place, shaping cosmic structures, and guiding the slow rotation of worlds. Without it, the universe you know would not look the same. It may not even exist in any recognizable form. If this quiet journey through invisible physics brings you even a moment of calm or wonder, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps keep these slow stories alive, and your presence means more than you know. Now, let's begin with the first truth. Part 1. What is holding the universe together? Right now, before we imagine dark matter vanishing, we need to understand what it is already doing. Every galaxy you've ever seen, every spiral arm, every glowing halo of stars is rotating faster than visible matter alone can explain. According to the equations of gravity, galaxies should tear themselves apart, and yet, they don't. Something unseen provides the missing mass, the quiet gravitational glue that keeps stars bound in vast, stable orbits. That invisible presence is dark matter, silently shaping the cosmos without ever revealing its face. To understand why this matters, imagine standing far above the Milky Way, watching it turn in slow motion. The galaxy spins once every few 100 million years, its spiral arms sweeping gracefully through space. The stars near the center move quickly, as expected, pulled tightly by the dense core. But farther out, something strange happens. Stars at the edge of the galaxy move just as fast as those closer in. They should be slowing down. Gravity, as we know it, weakens with distance, and yet the stars remain bound, circling calmly instead of flying off into the void. This contradiction is not subtle, it is profound. When astronomers first measured these motions, they expected the familiar pattern seen in our solar system, where distant planets orbit more slowly than those nearby. Instead, they found flat rotation curves, a steady speed maintained far beyond where visible matter could account for it. The equations were clear. Either gravity behaves very differently on large scales, or there is far more matter than we can see. Dark matter entered the story not as a bold idea, but as a reluctant necessity. It was the simplest explanation that fit the data, an invisible form of matter spread throughout and around galaxies, adding mass without adding light. This unseen mass forms vast halos, extending far beyond the glowing disks of stars. Inside these halos, galaxies live like lanterns suspended in a transparent ocean, their light tracing only the smallest fraction of what is truly there. You never feel this matter because it does not interact with you in familiar ways. It does not emit light. It does not absorb it. It does not collide with atoms or warm your skin. It reveals itself only through gravity, through the way it bends space and guides motion. Its presence is inferred, not observed. And yet without it, the universe would look nothing like it does now. On the largest scales, dark matter acts as the universe's scaffolding. In the early cosmos, just after the first atoms formed, matter was almost evenly spread. Tiny differences in density existed, barely noticeable ripples left over from the universe's beginning. On their own, ordinary matter would have struggled to clump together. Pressure from radiation and heat would have smoothed it out again. But dark matter, cold and slow-moving, began to gather in those slightly denser regions. These early clumps grew over time, pulling in surrounding material. Gas followed gravity's lead, flowing into invisible wells carved by dark matter. Where the wells were deepest, galaxies were born. Where they were shallower, smaller structures formed. The vast cosmic web you see in simulations today, filaments stretching across millions of light years, dotted with glowing nodes of galaxies, exists because dark matter laid down the framework first. Even now, long after the universe cooled, dark matter continues its quiet work. Galaxy clusters, the largest bound objects in existence, are held together primarily by it. If you were to count all the stars, all the gas, all the glowing material in a cluster, you would find it accounts for only a small fraction of the total mass. Most of what holds those hundreds or thousands of galaxies together is unseen. Remove it, and the cluster would slowly disperse, its galaxies drifting apart like embers cooling after a fire. There is another way dark matter makes itself known, even though it cannot be seen directly. Light, as it travels through space, follows the curves of space-time itself. When massive objects are present, space-time bends, and light follows those bends. This effect is gentle around stars, stronger around galaxies, and dramatic around clusters. Astronomers observe distant galaxies appearing stretched, doubled, or distorted, not because the light itself has changed, but because something massive lies between us and the source. When scientists map these distortions, they find mass where no visible matter exists. Entire regions of space act like gravitational lenses without any corresponding glow. These invisible concentrations trace the same structures predicted by dark matter models. Once again, gravity whispers the same answer. Something is there. What makes dark matter especially haunting is how little we know about its nature. It is not made of atoms. It does not form stars or planets. It does not clump into familiar shapes. It passes through ordinary matter almost without notice, like a shadow through fog. Billions of dark matter particles may be streaming through your body every second, leaving no trace of their passage. And yet, for all its elusiveness, dark matter behaves with remarkable discipline. It obeys gravity. It moves predictably. It forms structures over cosmic time. It does not collapse into disks like ordinary matter, because it cannot shed energy the way gas does. Instead, it remains diffuse, forming broad halos rather than sharp features. This difference is what allows galaxies to exist in their current form, bright, thin disks embedded in vast, invisible envelopes. If dark matter did not exist, gravity alone would struggle to explain why the universe looks the way it does. Galaxies might still form, but they would be smaller, rarer, and far less stable. Many would tear themselves apart as they spun. Others might never form at all. The long-lived, orderly cosmos we observe would be replaced by something thinner, more chaotic, and less hospitable to complexity. As you rest here now, it can be comforting to remember that stability often comes from what you cannot see. The universe is not held together by light alone or by what announces itself loudly. It is held together by quiet persistence, by invisible mass doing its work without recognition. Dark matter does not demand attention, it simply holds. And this realization gently reshapes perspective. The stars above you are not solitary actors burning bravely against emptiness. They are supported, guided, and constrained by something far larger and quieter than themselves. Every calm orbit, every stable galaxy, every long-lived structure owes its existence to an unseen partner. So when we ask what is holding the universe together right now, the answer is not dramatic. It is subtle, it is patient, it is invisible. Dark matter is not the universe's decoration, it is its foundation. And as we continue this quiet journey, one question naturally begins to rise. If something so essential can be hidden so completely, what else might the universe be doing just beyond our ability to see? Part 2. How do we know dark matter exists at all? Dark matter was not discovered by looking directly at it, but by watching how the universe behaves. In the 1930s, astronomers noticed that galaxies in clusters were moving far too quickly to remain bound by visible matter alone. Later, precise measurements of galactic rotation curves confirmed the mystery. Stars at the edges of galaxies orbit just as fast as those near the center, defying classical expectations. The simplest explanation was not new physics, but unseen mass spread like a halo around every galaxy. This way of discovering something invisible may feel unsettling at first. We are used to knowing things by seeing them, touching them, measuring them directly. But much of science, especially astronomy, works through consequences rather than contact. We infer what exists by how it shapes motion, bends light, and leaves patterns behind. Dark matter entered our understanding in this quiet, indirect way, not as a sudden revelation, but as a growing tension between theory and observation. In the early 20th century, astronomers began measuring the speeds of galaxies inside large clusters. These clusters are immense collections of hundreds or even thousands of galaxies, all bound together by gravity. According to the mass they could see, stars, gas, glowing clouds, the galaxies should not have been able to stay together. They were moving too fast. If visible matter were all that existed, the clusters should have dispersed long ago, their galaxies flying apart into deep space. And yet, they remained intact. This discrepancy was not small. It was overwhelming. The galaxies were behaving as if far more mass were present than anyone could account for. At first, this was treated cautiously. Instruments were still improving. Measurements could be wrong. But as decades passed, the data only grew stronger. The motions were real. The missing mass was unavoidable. The same pattern appeared closer to home, inside individual galaxies. When astronomers carefully mapped how fast stars orbit their galactic centers, they expected a familiar decline in speed with distance. That is how gravity behaves in systems dominated by a central mass, like planets orbiting a star. Instead, the speeds flattened out. Far from slowing down, stars continued moving at nearly constant velocity, even where there was little visible matter left to pull on them. This result was repeated again and again, across thousands of galaxies of different sizes and shapes. Spiral galaxies, dwarf galaxies, even galaxies with very little gas or dust showed the same behavior. The details varied, but the conclusion remained consistent. Something unseen was contributing most of the gravitational pull. At this point, scientists faced a choice. They could abandon the laws of gravity as we understand them, or they could accept that most matter in the universe does not emit light. Both options were explored seriously. Modified gravity theories were proposed and tested. Some could explain certain observations, but none could explain all of them at once. Dark matter, on the other hand, fit naturally into the growing web of evidence. Another powerful clue came from the way light travels across the universe. Light does not move through space in straight lines when gravity is present. Massive objects curve space-time, and light follows those curves. This effect, called gravitational lensing, allows astronomers to map mass by observing how background galaxies appear distorted. When scientists examined galaxy clusters using this technique, they found something remarkable. The strongest lensing effects often occurred in regions with very little visible matter. The mass doing the bending was not where the light was. It was somewhere else, invisible, but undeniably present. Entire maps of unseen mass could be reconstructed, revealing structures that matched predictions from dark matter simulations almost perfectly. In some rare cosmic events, this separation becomes especially clear. When galaxy clusters collide, their visible matter, hot gas glowing in X-rays, slows down and interacts. But the gravitational mass, traced through lensing, passes straight through, barely affected. The visible and invisible components part ways, like fog drifting apart from wind. These observations are among the clearest demonstrations that dark matter is not just an abstract idea, but a distinct physical component of the universe. Even the oldest light in existence carries its signature. The cosmic microwave background, the faint afterglow of the early universe, contains tiny variations in temperature. These variations encode information about how matter was distributed when the universe was only a few 100,000 years old. When scientists analyze this pattern, they find that the universe could not have evolved into its present structure without a large amount of non-luminous matter present from the beginning. Ordinary matter alone cannot explain the observed balance between hot and cold regions in this ancient light. Dark matter fits naturally into the equations, shaping how sound waves moved through the early cosmos and leaving an imprint that we can still detect today. This means dark matter is not a recent addition to the universe. It has been there since nearly the very beginning. What makes all of this especially compelling is how consistent the evidence is across vastly different scales. From the motion of individual stars, to the behavior of galaxies, to the structure of clusters, to the pattern of the early universe itself, the same invisible influence appears again and again. Each line of evidence is independent. Together, they form a quiet but overwhelming case, and still, dark matter refuses to show itself directly. Physicists have built sensitive detectors deep underground, shielded from noise, waiting for rare interactions between dark matter particles and ordinary atoms. So far, these experiments have seen nothing conclusive. Particle accelerators search for hints of dark matter creation. Space telescopes look for subtle signals that might betray its nature. The silence continues. But this silence does not weaken the case. In some ways, it strengthens it. Dark matter is defined by what it does not do. It does not glow. It does not clump like ordinary matter. It does not interact strongly with light or electromagnetism. Gravity is its language, and gravity alone has been enough to reveal its presence. There is something deeply humbling about this way of knowing. It reminds us that reality is not obligated to announce itself clearly. Much of what shapes existence operates quietly, beyond the reach of direct perception. We learn by watching patterns unfold, by listening to motion, by trusting the consistency of nature's laws. As you rest here now, it may feel comforting to know that certainty in science does not always come from sight. It comes from coherence, from many small pieces fitting together without contradiction. Dark matter is not believed in because it is mysterious. It is accepted because without it, the universe stops making sense. And so, even though we cannot see it, dark matter stands as one of the most well-supported components of modern cosmology. It is written into the rotation of galaxies, the bending of light, the oldest radiation in the sky. It is present not as an image, but as a pattern. And as we continue this quiet journey, another question naturally follows. If dark matter reveals itself only through motion and gravity, what would happen if that influence were suddenly removed? What would the universe do when its invisible foundation quietly disappeared? Part 3. What would happen the instant dark matter disappeared? If dark matter vanished suddenly, there would be no explosion, no flash of light, no immediate sound. Instead, gravity itself would quietly weaken across the universe. The invisible scaffolding holding galaxies together would dissolve in silence. Stars would not stop moving, but their paths would begin to drift, no longer guided by the hidden mass that once steadied their motion. The change would be subtle at first, unfolding over millions of years, but it would be irreversible. To understand this moment, it helps to slow time down in your mind. Imagine the universe as it is right now. Galaxies turning, clusters breathing gently with gravity, stars following ancient paths carved long before Earth existed. In this first instant after dark matter disappears, nothing dramatic announces the change. Every star keeps moving exactly as it was a moment before. Every planet continues its orbit. The night sky looks the same. Gravity does not turn off, it simply becomes weaker than it was meant to be. For billions of years, stars and galaxies have been moving too fast for visible matter alone to hold them. Dark matter supplied the missing pull, balancing motion with mass. When that unseen mass vanishes, the balance is broken. But motion has memory. Stars do not suddenly fall away or collide. They continue forward, carrying the momentum they already have. At first, the difference is almost impossible to notice. A star near the edge of a galaxy might drift outward just slightly more than before. Its orbit becomes a little wider, a little less bound. Over thousands of years, this change is still subtle. Over millions, it becomes undeniable. Galaxies are not solid objects. They are delicate gravitational arrangements held together not by structure, but by continuous balance. Remove enough mass and that balance unravels slowly, like a knot loosening over time rather than snapping all at once. Spiral arms begin to stretch. Their graceful curves lose definition as stars slip outward, no longer confined to the paths that once shaped them. Near the centers of galaxies, where visible matter is densest, gravity remains relatively strong. Those regions hold together longer. But farther out, where dark matter once dominated, stars begin to escape. They do not rush away. They drift, gently peeling off into intergalactic space, becoming solitary travelers in a widening cosmos. this is not destruction as we usually imagine it. There is no violence, no shockwave. It is a quiet dispersal, a slow thinning. As galaxies lose stars, they also lose their ability to form new ones. Star formation depends on gravity compressing clouds of gas until they ignite. With less mass overall, those clouds struggle to collapse. Regions that once sparkled with stellar nurseries grow still. The universe does not go dark immediately, but it stops renewing itself. What exists continues. What does not yet exist never will. On larger scales, the effects deepen. Galaxy clusters, already fragile arrangements, begin to dissolve. The galaxies within them drift apart, their mutual gravity no longer strong enough to keep them bound. Over billions of years, clusters spread into loose associations, then into isolation. The cosmic web, once traced by dark matter filaments, begins to fade as its underlying structure disappears. Even the shape of the universe changes in character, not in size but in texture. Where once matter gathered into knots and threads, now it smooths out. The universe becomes more uniform, more evenly spread, less structured. Complexity gives way to simplicity. And still, through all of this, time moves quietly forward. If you were living on a planet during this transformation, you would not notice it within a lifetime. Your sun would still shine. Your world would still turn. Dark matter plays almost no role in the day-to-day mechanics of a solar system. Its absence would not shake your ground or alter your sky overnight. But the future of your galaxy would already be changing. Over tens of millions of years, the stars visible in your night sky would subtly rearrange. Familiar constellations would distort. The dense band of the Milky Way would thin as stars escaped its grip. Eventually, your galaxy would no longer be a spiral at all, but a fading, irregular cloud, slowly dispersing into the darkness between galaxies. On the grandest scales, the universe grows quieter. Expansion, driven by dark energy, continues as before. But now there's less resistance. Fewer massive structures slow it locally. The universe does not accelerate dramatically faster, but it empties more efficiently. Space grows larger while matter becomes more isolated. This scenario reveals something profound about gravity. Gravity does not pull objects together in a static way. It is a dynamic relationship between mass and motion. Dark matter was not simply adding weight, it was shaping the paths that motion could take. Without it, motion wins, and motion, once unbound, does not easily return. There is also a deeper consequence, one that reaches back to the earliest moments of the universe. Dark matter did not just hold things together later. It helped build them in the first place. Without it, the universe would struggle to create structure at all. Galaxies would be smaller, rarer, and shorter-lived. Remove it now, and you are not just changing the future. You are erasing the conditions that allowed the past to happen. In this sense, the disappearance of dark matter is not just a loss of mass, it is a loss of history's foundation. And yet, there is a strange calm in this vision. The universe does not rage against the change. It adapts, it drifts, it unfolds according to the rules that remain. Physics does not mourn what is gone, it simply recalculates. As you breathe right now, consider how much of reality depends on things you cannot see. The stability you feel, of ground beneath you, of stars above you, is supported by layers of influence that never announce themselves. Dark matter is one of those layers. Remove it, and the universe does not scream. It sighs, slowly loosening its grip. And this raises a final gentle thought. If the most dramatic transformation imaginable can happen without spectacle, without sound, without light, then perhaps change itself is not always something to fear. Sometimes it is simply the quiet result of balance shifting. As this section comes to rest, one question remains suspended in the dark. If the universe can slowly unravel when its invisible foundation is removed, what does that tell us about how fragile or how resilient cosmic order truly is? Part 4. Would the Milky Way fall apart? Our galaxy is wrapped in a vast halo of dark matter extending far beyond its visible stars. This halo stabilizes the Milky Way's graceful spiral, keeping its 100 billion stars in long-lived orbits. Without dark matter, the galaxy would lose much of its gravitational cohesion. Over time, stars near the edges would escape into intergalactic space, while the spiral structure itself would slowly unravel, fading into a loose, distorted cloud of stars. To feel what this means, imagine the Milky Way not as a picture, but as a living system in motion. From above its disk, the galaxy turns slowly, its spiral arms winding like pale ribbons through space. These arms are not solid things, they are patterns, regions where stars linger a little longer, guided by gravity's steady hand. Dark matter is the unseen weight that steadies that hand, shaping the overall rhythm of the rotation. Without it, the rhythm falters. In the inner regions of the Milky Way, where stars crowd together and gas clouds glow, gravity remains relatively strong. Billions of suns orbit close to the galactic center, bound tightly by the mass they can see. These inner regions would endure the longest. For a time, they might even look unchanged. The familiar glow of the galactic core would still shine. The dense star fields would still sparkle. But the outer disk tells a different story. Far from the center, where stars are spaced more widely and visible matter thins out, dark matter dominates the gravitational landscape. It is here that the halo does most of its work, keeping stars moving fast without letting them drift away. When that halo vanishes, those stars are the first to feel unmoored. They do not fall outward. They simply keep going. Each star already has motion, tens or hundreds of kilometers per second, inherited from the galaxy's rotation. With less gravity pulling them inward, their orbits stretch. What were once gentle looping paths become long arcs. Some stars swing wide and never return. Others settle into new, broader orbits that no longer trace a spiral. Over millions of years, the disk thins. The outer arms lose definition, their elegant curves dissolving into streams. The Milky Way's iconic spiral shape, something that took billions of years to form, begins to fade, not abruptly, but patiently, as if the galaxy is exhaling. As stars escape, the galaxy grows dimmer from the outside in. The night sky seen from within would slowly change. The dense river of light we call the Milky Way would appear narrower, less bright. The sense of being embedded in a vast luminous disk would weaken as stars drift farther apart. Star formation would also suffer. Spiral arms are not just visual features, they are engines of creation. They compress gas clouds, triggering the birth of new stars. As the spiral pattern dissolves, these compression zones weaken, gas spreads out, clouds fail to collapse. Fewer stars are born to replace those that age and die. The galaxy, once dynamic and renewing, enters a quieter phase. Over longer spans of time, even the inner regions begin to change. As mass leaks away from the outskirts, the overall gravitational potential of the Milky Way decreases. The core subtly expands, orbits rearrange. The tight harmony between stars loosens, though it never becomes chaotic. Gravity still operates. It simply has less to work with. Eventually, the Milky Way is no longer a spiral galaxy at all. It becomes something more diffuse, a loose association of stars sharing a common origin, but no longer bound in a crisp, rotating structure. From a distance, it would resemble a faint, irregular glow rather than a majestic pinwheel. And yet, it would not truly fall apart in the way the word suggests. There is no moment of collapse, no catastrophic tearing. The galaxy does not shatter, it disperses. This distinction matters. Nature rarely destroys by sudden violence on cosmic scales. More often, it transforms by slow redistribution. Energy and motion find new configurations. The Milky Way, deprived of its dark matter halo, simply finds a new equilibrium, one that is broader, thinner, and less structured than before. From the perspective of a star like our Sun, the change would be almost imperceptible for a very long time. The Sun orbits far from the galactic center, but not at the very edge. Its path would gradually stretch, its period lengthening slightly. The familiar background of stars would subtly shift over millions of years, but nothing would announce itself as a disaster. Life on Earth, if it still existed, would not notice the galaxy's slow unraveling. Seasons would continue, orbits would remain stable. The Milky Way's transformation would be a backdrop, not a threat. But on cosmic timescales, the difference is profound. The Milky Way, as a distinct, recognizable galaxy, would cease to exist. Its identity would blur. The stars that once shared a coherent dance would become lonelier, more isolated, drifting through a growing ocean of space. There is something quietly humbling in this image. We tend to think of galaxies as permanent fixtures, as ancient and unchanging. But even they depend on delicate balances. Remove one key component and their grandeur slowly dissolves. Dark matter, in this sense, is not just extra mass, it is memory. It preserves the shape of galaxies across billions of years. It allows patterns to endure long enough for complexity to arise, for heavy elements to form, for planets to assemble, for life to take hold under steady skies. Without it, the Milky Way still exists, but only briefly by cosmic standards. Its beauty becomes transient. And this leads to a gentle realization: the stability you inherit, the predictable night sky, the long history of stars before you, rests on foundations you never see. The galaxy above you is not held together by what shines, but by what remains hidden. As we drift onward in this quiet exploration, one question lingers softly. If even a galaxy as vast as the Milky Way can slowly lose its shape when an invisible support is removed, what does that say about the delicate balances that hold all things together, both in the cosmos and perhaps within ourselves? Part 5. What happens to stars? When gravity weakens, stars are born inside dense clouds of gas that collapse under gravity. Dark matter plays a quiet role here too, helping those clouds gather and compress in the first place. Without it, fewer stars would form. Existing stars would continue to burn for billions of years, but their galactic neighborhoods would thin. Star systems would drift farther apart, and the rich stellar cities of the universe would slowly become sparse and isolated. To understand this change, it helps to think of gravity not as a force that switches on or off, but as a gentle pressure that guides matter into patterns. Stars are not created in isolation. They emerge from vast molecular clouds, cold, diffuse regions of gas drifting through galaxies. Left alone, these clouds would remain thin and scattered, never dense enough to ignite. Gravity is what gathers them, coaxing particles closer until heat and pressure trigger nuclear fusion. Dark matter does not ignite stars directly. It does something quieter. It shapes the environments where star formation becomes possible. By adding mass to galaxies, it deepens their gravitational wells, allowing gas to collect and remain bound long enough to cool and collapse. It creates the stillness required for creation. When gravity weakens on galactic scales, that stillness becomes harder to find. In a universe without dark matter, gas clouds struggle to gather. They drift, stretch, and disperse before they can collapse. Collisions between clouds become rarer as stars and gas spread farther apart. The raw material for star formation still exists, but the conditions needed to transform it into light become scarce. The stars that already exist, however, are patient. Once ignited, a star is remarkably resilient. Its gravity is generated by its own mass, not by the galaxy around it. Nuclear fusion in its core continues steadily, converting hydrogen into helium, releasing energy that balances the inward pull of gravity. This balance can last billions of years, so stars do not go out when gravity weakens elsewhere. They simply find themselves more alone. As galaxies disperse and thin, the distances between stars increase. Stellar neighborhoods that once felt crowded begin to empty. Regions rich with star clusters slowly dissolve as gravity can no longer hold them tightly together. Clusters stretch into streams. Streams fade into solitary points of light. In such a universe, the night sky would change its character. From any given vantage point, fewer stars would be close enough to shine brightly. The sky would not go dark, but it would lose depth. The sense of being surrounded by countless suns would soften into something quieter, more distant. Star formation slows not with a sudden stop, but with a gradual decline. Each generation of stars leaves behind heavier elements, carbon, oxygen, iron, essential ingredients for planets and life. With fewer new stars forming, this chemical enrichment slows. The universe continues aging, but it stops growing richer in complexity. Over very long timescales, this has profound consequences. The most massive stars, which live fast and die young, become rarer. Supernovae, those brilliant explosions that seed space with heavy elements, occur less often. The universe grows calmer, less energetic, less luminous. Even the distribution of star types shifts. Long-lived, low-mass stars come to dominate. Red dwarfs, already the most common stars, become even more prevalent relative to their brighter cousins. These stars burn quietly for trillions of years, providing steady but faint light. The universe enters a long, dim twilight phase much earlier than it otherwise would. Yet there is no sense of failure in this transformation. Physics does not judge. It simply follows its rules to their natural conclusion. When gravity weakens, creation becomes harder, not impossible. The universe does not stop making stars entirely. It just makes them more rarely, more carefully. There is something deeply meditative about this slowdown. It mirrors processes closer to home. Growth requires conditions to align. Energy, structure, and balance must come together. When one ingredient fades, the system adapts by becoming quieter rather than collapsing. From the perspective of a single star, none of this is alarming. A star lives its life unaware of the galaxy's fate. It burns steadily, its internal processes unchanged. If it hosts planets, those planets continue their orbits, warmed by starlight that has no knowledge of cosmic drift. But for the universe as a whole, the weakening of gravity marks a shift from abundance to scarcity, from crowded brilliance to spacious calm. The phrase stellar cities is not just poetic. Galaxies truly are cities of stars, with dense centers, sprawling suburbs, and intricate patterns of motion. Dark matter is the infrastructure that keeps those cities connected. Remove it, and the city does not explode. It slowly empties. Buildings remain, lights stay on, but the distances between neighbors grow until silence fills the streets. And yet, even in this thinning universe, there is continuity. Light still travels, fusion still burns, time still flows. The cosmos becomes more spacious, more minimal, but not empty. As you rest here, consider how much of existence depends on gentle accumulation rather than force. Stars are born not through violence, but through patience, through gravity's quiet insistence over millions of years. When that insistence weakens, the universe does not rebel. It simply breathes out, becoming simpler. This perspective offers a kind of comfort. It reminds us that endings in the universe are rarely abrupt. They are gradual, giving space for adaptation, for long afterglows of light to continue shining. And so, as this chapter draws to a close, one soft question remains. In a universe where gravity weakens and stars grow lonelier, what new kind of calm emerges from that vast, widening silence? Part 6. Would planets and solar systems be affected? On human timescales, your planet would feel almost nothing. Dark matter's influence within a solar system is incredibly small compared to the gravity of stars and planets. Earth would continue to orbit the sun, the moon would still rise and fall. But on cosmic timescales, the larger structure containing our solar system, the Milky Way itself, would change. And eventually, that larger change would matter. To understand why, it helps to picture where dark matter actually is. Although it surrounds galaxies in enormous halos, it is spread extremely thinly. Even here within the Milky Way, dark matter passes through the solar system in a diffuse stream, contributing almost nothing to the local gravitational balance. The motions of planets are governed by the sun. The motion of the moon is governed by Earth. These systems are intimate, tightly bound, and largely self-contained. If dark matter vanished tomorrow, nothing in the sky would announce it. Your day would still begin with sunrise. Seasons would still unfold. The careful clockwork of orbital mechanics would continue uninterrupted. The equations describing planetary motion would not suddenly change because they were never relying on dark matter in the first place. This is one of the quiet truths of the universe. The forces that shape the largest structures often have little influence on the smallest, and vice versa. A galaxy depends on dark matter. A solar system does not. For a very long time, this separation remains comforting. Stars continue to host planets. Planets continue to trace stable paths. Life, if it exists, remains sheltered by local gravity. The weakening of galactic scale gravity does not ripple inward like a shock wave. It takes its time. But gravity is a hierarchy. Local systems exist within larger ones. Solar systems orbit stars. Stars orbit galactic centers. Galaxies orbit within clusters. When a higher level of that hierarchy begins to dissolve, the lower levels eventually feel the change, not as a sudden disruption, but as a slow drift. As the Milky Way's structure weakens, the Sun's path around the galaxy begins to change. Its orbit grows less defined. Instead of circling a well-shaped spiral, it follows a more extended, wandering trajectory. Over hundreds of millions of years, the Sun may find itself farther from the galactic center, or even on a path that slowly leads it away from the remaining stellar core. For planets like Earth, this has no immediate consequence. The Sun remains their anchor. But the environment surrounding that anchor changes. The density of nearby stars decreases. Stellar encounters become rarer. The gravitational nudges that occasionally reshape distant comet clouds weaken. Even the outermost regions of a solar system, such as the Oort cloud, feel this change first. These distant reservoirs of icy bodies are only loosely bound to their stars and are more sensitive to the galaxy's gravitational field. As the galactic pull weakens, some of these objects drift away, becoming interstellar wanderers. This does not threaten inner planets, but it subtly alters the long-term evolution of planetary systems. Over vast spans of time, as galaxies disperse and stars become more isolated, solar systems transition from being members of bustling stellar communities to solitary islands. The sky from any given planet grows emptier. Fewer nearby stars pass close enough to be noticeable. The night becomes quieter. This isolation has both gentle and profound effects. On one hand, fewer stellar encounters mean greater long-term stability. Planetary orbits become less likely to be disturbed by passing stars. On the other hand, the flow of material between systems, comets, dust, and interstellar debris, slows. The exchange of matter that once subtly connected stars across a galaxy diminishes. For life, this shift is ambiguous. Isolation can be protective. It can also be limiting. The universe becomes less interactive, more compartmentalized. As the Milky Way continues to thin, the Sun may eventually no longer be part of a recognizable galaxy at all. It would still have its planets. It would still shine. But it would travel through space without a clear galactic identity, accompanied by only the faint glow of distant, scattered stars. From Earth's perspective, if it still existed, the Milky Way would no longer stretch across the sky as a luminous band. Instead, the sky would be dominated by the Sun by day, the Moon by night, and only a sparse sprinkling of stars beyond. The sense of being embedded in a vast cosmic city would be replaced by the feeling of deep space, yet nothing about planetary motion itself would break. This is an important distinction. Dark matter does not hold planets together. It does not keep moons in place or guide asteroids through their paths. The local dance of gravity remains intact. This resilience speaks to a deeper truth. Stability in the universe often comes from layers. When one layer fades, others continue. Solar systems are remarkably self-sufficient. They can survive long after their galactic homes have changed beyond recognition. There's a quiet reassurance in this. It suggests that life, once established, does not depend on the entire universe remaining unchanged. It depends on local balance, on the steady burn of a star, on the reliable pull of gravity between nearby bodies. But there is also a poignant reminder. Even the most stable systems are part of something larger. The context around them shapes their story, even if it does not control their every step. As you rest now, imagine the patience of planetary motion. Each orbit is a promise kept repeated billions of times without complaint. These motions continue even as galaxies disperse and cosmic structures thin. They are small, but they are enduring. And so, as this chapter gently settles, one final thought remains. If planets and solar systems can persist quietly while the universe around them transforms, what does that tell us about the balance between change and continuity in the cosmos? Part 7. What happens to galaxy clusters? Galaxy clusters are the largest gravitationally bound structures in the universe, and they are dominated by dark matter. Remove it, and the delicate balance holding hundreds or thousands of galaxies together would fail. Over billions of years, galaxies would drift apart, escaping the weakened gravitational wells that once held them. The universe would become emptier, quieter, and more spread out than ever before. To understand why galaxy clusters matter so deeply, imagine zooming out farther than ever before, past individual stars, past entire galaxies. You arrive at a scale where gravity has spent billions of years gathering not just light, but entire islands of stars into vast communities. Galaxy clusters are these communities, the cosmic cities of cities. They are bound together not by chance, but by immense reservoirs of mass that far outweigh everything you can see. In a typical cluster, the glowing matter, stars, gas, dust, accounts for only a small fraction of the total mass. The rest exists in silence. Dark matter fills the space between galaxies, forming a deep gravitational basin in which hundreds or thousands of galaxies orbit, much like stars orbit within a galaxy. This invisible mass is what keeps clusters intact across cosmic time. Without it, the cluster's cohesion begins to loosen. At first, the change is subtle. Each galaxy continues along its path, unaware that the gravitational landscape beneath it has shifted. Motion carries on, orbits persist. But just as with stars in a galaxy, the balance between motion and gravity has been altered. Galaxies are moving too fast for visible matter alone to hold them together. Unlike stars, however, galaxies are enormous systems with their own internal gravity. They do not disintegrate when the cluster weakens. Instead, they begin to drift relative to one another. The cluster, once a tightly bound structure, becomes more like a loose association. Over hundreds of millions of years, the outskirts of the cluster thin first. Galaxies on the edges, already weakly bound, slowly peel away. They follow elongated trajectories that no longer curve back inward. They escape quietly, joining the vast intergalactic spaces between clusters. The core of the cluster holds on longer. There, galaxies are closer together, and visible matter plays a slightly larger role. But even this central region cannot maintain its integrity indefinitely. As mass leaks away from the outskirts, the overall gravitational pull weakens further. The cluster expands, its galaxies spreading out, their interactions becoming rarer. Galaxy clusters are not static objects. Even now, they evolve, merge, and accrete new members along filaments of the cosmic web. Dark matter is the reason those filaments exist at all. It traces long, thread-like structures across the universe, guiding matter into clusters like rivers flowing into seas. When dark matter disappears, those filaments fade. The cosmic web begins to dissolve, not by snapping apart, but by losing definition. Matter spreads more evenly. The universe's large-scale structure smooths out. The dramatic contrast between dense clusters and vast voids softens into a more uniform distribution. In this process, the universe loses one of its most striking features: scale hierarchy. Today, matter is arranged in layers: stars within galaxies, galaxies within clusters, clusters within superclusters. Dark matter makes this nesting possible. Without it, the layers flatten. The universe becomes simpler in structure, less richly organized. There is also an energetic consequence. Galaxy clusters are filled with hot gas, heated by gravity as it falls into deep potential wells. This gas emits X-rays, making clusters some of the brightest extended objects in the universe at high energies. As the gravitational wells weaken, this gas slowly escapes. It cools and disperses, dimming the clusters further. The universe does not just become emptier in terms of matter, it becomes quieter in terms of energy. Collisions between galaxies within clusters grow rare, mergers slow. The dramatic reshaping events that once triggered bursts of star formation and black hole growth diminish. The universe enters a calmer phase, where change still occurs, but at a gentler pace. From a philosophical distance, this transformation feels almost like a cosmic aging. Youth is marked by structure, interaction, and density. Old age brings expansion, separation, and stillness. The disappearance of dark matter accelerates this aging process, pushing the universe toward a state of wide, peaceful isolation. And yet, nothing truly disappears. Galaxies that escape clusters do not vanish. They continue their journeys through space, carrying their stars, planets, and histories with them. They simply no longer belong to a larger collective. If you could watch this process unfold from far away, you would see clusters slowly unraveling, their galaxies drifting like leaves released from a gentle current. No violence, no urgency, just motion continuing without restraint. There is something deeply consistent about this behavior. Gravity does not enforce order forever. It negotiates balance. When mass is removed, balance shifts, motion finds new paths, the universe adapts without complaint. As you listen now, perhaps this image resonates in an unexpected way. Structures, cosmic or personal, often rely on unseen supports. When those supports weaken, the structure does not always collapse dramatically. Sometimes it simply loosens, allowing its parts to move more freely. Galaxy clusters teach us that even the largest bonds are conditional. They exist not because they must, but because the conditions allow them to. Remove those conditions, and the bonds relax. Over trillions of years, a universe without dark matter would be one where clusters are memories rather than realities. The great congregations of galaxies that once dominated cosmic maps would be replaced by a quiet sea of isolated systems, each tracing its own path through an ever-expanding space. And yet, this quieter universe is not empty. It is spacious. It offers room rather than confinement. It trades density for calm. As this chapter gently fades, one question drifts into focus. If the universe can transition from tightly bound clusters to vast, peaceful isolation simply by losing an invisible component, what does that suggest about the balance between connection and freedom woven into the fabric of reality itself? Part 8. Would the universe stop making new galaxies? Dark matter played a crucial role in the early universe, forming dense regions that acted as seeds for galaxies. Without it, matter struggles to clump together. If dark matter disappeared early enough, galaxies might never form at all. If it vanished now, the era of galaxy formation would effectively end. The universe would age without renewal, carrying only the structures already built. To understand why this matters, we have to drift backward to a time when the universe was young and simple. In its earliest moments after the first atoms formed, matter was spread almost evenly through space. There were no stars, no galaxies, no glowing islands of light, just a cooling fog of hydrogen and helium expanding steadily with the universe itself. Left alone, that fog would have remained nearly uniform. Gravity would have tried to pull matter together, but ordinary matter resists collapse. As gas falls inward, it heats up. That heat creates pressure, pushing outward, fighting gravity's pull. Without something to tip the balance, collapse stalls. Structure never quite begins. Dark matter was that tipping point, because dark matter does not interact with light or heat. It does not build up pressure in the same way. It cools efficiently, not by losing energy, but by never gaining much in the first place. In the early universe, dark matter began to clump first, gathering into faint, invisible concentrations long before ordinary gas could follow. These concentrations were small at first, tiny ripples in an otherwise smooth universe. But gravity is patient. Over millions of years, those ripples grew. Where dark matter gathered, space-time curved more deeply. Ordinary matter felt that curvature and slowly drifted in, like mist settling into shallow valleys. This is how the first galactic seeds formed. Without dark matter, those valleys would not exist. Gas would drift, expand, and thin faster than gravity could organize it. The universe would remain a diffuse haze, glowing faintly but never condensing into stars or galaxies. Light would exist, but structure would not. If dark matter vanished very early in cosmic history, before these seeds could grow, the universe might never have progressed beyond this stage. No galaxies, no long-lived stars, no complex chemistry. The cosmos would be smooth, simple, and largely dark. But if dark matter vanished later, after galaxies had already formed, the story changes. The universe would not suddenly erase what it had built. Existing galaxies would persist for a time, slowly evolving as we've already explored. But the process that creates new galaxies would shut down. The cosmic assembly line would stop. In today's universe, galaxies still form, though much more slowly than they once did. Small galaxies merge to make larger ones. Gas flows along dark matter filaments into growing systems. Star formation flickers to life in regions where gravity and cooling align just right. Remove dark matter, and these processes stall. Without the deep gravitational wells provided by dark matter, gas struggles to fall inward. Instead of streaming efficiently into forming galaxies, it disperses. The density thresholds required for collapse are rarely reached. New galaxies fail to ignite, even mergers slow. Galaxies still encounter one another, but without the extended halos of dark matter to guide and capture them, many fly past instead of combining. Growth becomes inefficient. Assembly becomes rare. The universe enters a maintenance phase rather than a creative one. What already exists continues to age. Stars burn, galaxies drift. But nothing fundamentally new appears on large scales. The universe carries its existing structures forward like heirlooms, not investments. This shift has a subtle emotional texture to it. It is not catastrophic, it is autumnal. The universe does not collapse, it does not explode, it simply stops building. Like a city that no longer constructs new neighborhoods but maintains its old streets until they slowly empty, the cosmos becomes a place of inheritance rather than expansion. Over billions of years, this has compounding effects. As stars age and die, fewer new stars replace them. As galaxies thin and disperse, fewer environments remain where gas can be recycled efficiently. The cosmic rhythm slows. There's also a profound asymmetry here. Dark matter was essential for creation, but not strictly required for persistence. This tells us something important about how the universe works. Building structure is harder than maintaining it. Creation requires precise conditions. Continuation requires far less. This is why the loss of dark matter feels quiet rather than violent. The universe is not undone, it is simply no longer renewed. If you were to observe this future cosmos from a great distance, you would see fewer bright, youthful galaxies. Most systems would appear older, redder, dominated by long-lived, low-mass stars. The blue glow of star formation would be rare. The universe would feel settled, even tired. Yet it would not be dead. There would still be motion, still light, still time. The universe would continue expanding, carrying its remaining structures farther apart. Space would grow larger around fewer luminous anchors. This perspective invites a deeper reflection. We often imagine the universe as endlessly productive, constantly generating new wonders. But in reality, it has phases. Periods of rapid creation followed by long eras of quiet evolution. Dark matter was the catalyst that allowed the universe to have a rich, structured youth. Without it, that youth ends sooner. As you rest here, consider how much of what you value, complexity, richness, variety, depends on early conditions aligning just once. The universe did not get multiple chances to set itself up. It had to succeed early, or not at all. Dark matter made that success possible. And now, as we imagine it fading away, we see a universe that continues, but does not reinvent itself. A universe that remembers, rather than creates. As this chapter gently comes to rest, one final question emerges. In a cosmos that can no longer build new galaxies, what becomes most precious, the act of creation itself, or the quiet endurance of what already exists? Part 9. How would cosmic expansion change? Dark matter works alongside dark energy. the force driving cosmic expansion. While dark energy pushes space apart, dark matter helps resist that expansion locally, allowing galaxies and clusters to exist. Remove dark matter, and expansion would gain the upper hand more easily. The universe would not explode outward, but its large-scale structures would lose their resistance, thinning more rapidly over time. To feel this change, it helps to imagine expansion not as motion through space, but as space itself slowly stretching. Every second, the distance between faraway galaxies increases, not because they are flying away, but because the fabric beneath them is gently growing. This expansion has been happening since the universe began, but its influence has not always been dominant. For much of cosmic history, gravity held its ground. In the early universe, matter, both visible and dark, was dense enough to slow expansion locally. Regions of higher mass resisted the stretching of space, allowing galaxies and clusters to form and remain intact. Dark matter was especially important here. Because it outweighed ordinary matter by such a large margin, it provided most of the gravitational resistance needed to counter expansion on large scales. Dark energy, by contrast, is subtle. It does not clump. It does not pull. It acts everywhere at once, evenly, like a quiet pressure urging space to grow. For billions of years after the Big Bang, this pressure was present but weak compared to gravity's grip. Only when the universe became large and diffuse enough did dark energy begin to dominate. We live in that era now. Even today, gravity still wins locally. Galaxies remain bound, clusters persist. The Milky Way is not being torn apart by expansion because the combined mass of its stars and dark matter holds it together. Expansion is something that matters only on the largest scales, far beyond individual systems. But remove dark matter, and this balance shifts. Without dark matter, gravity's ability to resist expansion weakens dramatically, not everywhere at once and not instantly, but inevitably. The universe does not suddenly race outward faster. Instead, fewer regions remain dense enough to hold themselves together against the steady stretching of space. In a universe without dark matter, expansion becomes less contested. Clusters disperse more quickly. Galaxies drift apart more easily. The distance between large structures increases faster than it otherwise would, not because expansion itself accelerates dramatically, but because there is less mass to oppose it. The same expansion, meeting less resistance, reshapes the cosmos more efficiently. This distinction is important. Dark energy sets the pace of expansion. Dark matter sets the texture of what expansion acts upon. Remove dark matter, and expansion smooths the universe more thoroughly. Over billions of years, this leads to a cosmos with fewer anchors. Large structures dissolve into smaller ones, then into isolated systems. Expansion stretches the spaces between them until interactions become rare, then negligible. The universe becomes not just larger, but emptier in practice. From a distance, this future cosmos would look different from ours. Today, the universe is richly structured, with bright clusters and dark voids forming a complex pattern. In a dark matter-free universe, that contrast softens. Matter spreads more evenly. Voids expand, filaments fade, the cosmic web loses its definition. Expansion does not destroy matter, it dilutes it. As space grows, energy density drops, radiation thins, matter becomes less influential. Dark energy, constant per unit volume of space, grows relatively more important. Its quiet dominance becomes more complete. Eventually, expansion defines the universe's character almost entirely. This process has a subtle emotional quality to it. It is not dramatic, it is not violent, it is spacious. The universe does not rush toward an ending. It drifts toward stillness. Time continues, light continues, but the chances for interaction diminish. Even light itself begins to feel the change. As galaxies drift farther apart, their light takes longer to reach one another. Some galaxies recede so quickly that their light can never arrive at distant observers. Horizons form, not because of speed through space, but because of space expanding between points faster than light can traverse. In such a universe, isolation becomes the norm. Each remaining galaxy, each star system, exists within its own expanding bubble of space, increasingly disconnected from the rest. The universe is still one whole, but functionally, it becomes many quiet regions, each unaware of the others. Dark matter once helped delay this fate. By holding matter together, it created long-lived structures that resisted isolation. It allowed galaxies to remain neighbors for billions of years. Without it, separation comes sooner. And yet, there is no sense of urgency in this transformation. Expansion is patient. It works over timescales far beyond human imagination. The thinning of the universe unfolds so slowly that no single moment marks the change. There is no day when the cosmos feels different. Only eons later does the pattern reveal itself. As you breathe now, it may be comforting to remember that expansion does not erase what exists. It only stretches the context around it. A star remains a star. A planet remains a planet. A moment remains a moment. But the story connecting those moments grows quieter. This raises a deeper reflection about the nature of resistance. Dark matter did not stop expansion. It negotiated with it. It slowed it locally, shaped it, gave it form. Remove that negotiation, and expansion proceeds more cleanly, more uniformly, less hindered by structure. In this way, dark matter can be thought of as the universe's texture, what gives expansion something to work against. Without it, expansion becomes smoother, simpler, more absolute. There is a quiet elegance in this outcome. The universe does not cling, it does not fight, indefinitely. When resistance fades, it yields gracefully. As this chapter settles into silence, one last question drifts gently forward. In a universe where expansion gradually overcomes structure, where space grows larger while connections fade, what remains most meaningful? The vastness itself, or the rare moments when matter once gathered closely enough to shine together? Part 10. Would light travel differently without dark matter? Dark matter bends space-time, subtly curving the paths of light through a phenomenon known as gravitational lensing. Astronomers use this effect to map dark matter's distribution. Without it, the universe would appear optically simpler. Light would travel more directly, revealing fewer distortions, but also fewer clues. The cosmos would become easier to see, yet poorer in structure. To understand this change, it helps to pause and consider what light actually does as it moves through the universe. Light does not simply pass through space as a straight arrow, it follows the geometry of space-time itself. Wherever mass exists, space-time curves, and light quietly obeys those curves, bending without friction, without sound, without resistance. Dark matter, though invisible, is massive. Spread across galaxies and clusters, it creates broad, gentle curvatures in space-time, too subtle to notice by eye, but strong enough to redirect light traveling for billions of years. When astronomers observe distant galaxies whose light has passed through these regions, they see arcs, smears, duplicated images. The universe appears warped, as though viewed through a glass that no one can see. This warping is not a flaw in the cosmos, it is a signature. Gravitational lensing has become one of the most powerful tools in modern astronomy, precisely because it does not rely on light being emitted. It relies only on gravity. Where light bends, mass must be present. And again, lensing reveals mass where nothing shines. Without dark matter, this entire layer of the universe's visual language would fade. Light would still bend near stars, planets, and black holes. Those effects would remain. But the vast diffuse lensing caused by galaxy halos and clusters would largely disappear. The long arcs tracing invisible filaments would no longer stretch across the sky. Distant galaxies would appear closer to their true shapes, less distorted, less magnified. At first, this might sound like a gift. The universe would become clearer, more straightforward. Objects would appear where they actually are, images would be easier to interpret, the sky would feel calmer, less twisted by unseen forces. But clarity comes with loss. Gravitational lensing does more than distort. It reveals, it magnifies faint objects, allowing us to see galaxies that would otherwise be too dim or too distant to detect. Some of the earliest galaxies ever observed were found not because they were bright, but because dark matter lenses amplified their light. Without Dark matter, these natural telescopes, vanish. The distant universe becomes harder to explore. The faintest structures slip beyond reach. The deep past grows quieter, more hidden. Light still travels, but it carries less information forward. There is also a subtle change in how space itself feels. Lensing adds texture to the cosmos. It makes space uneven, layered, rich with invisible contours. Remove dark matter, and space-time smooths out on large scales. The universe becomes more uniform, less sculpted. Light paths become simpler because the space they traverse is simpler. Over vast distances, this has cumulative effects. Light arriving from the edge of the observable universe would follow straighter routes, encountering fewer gravitational valleys and hills. Travel times might differ slightly. The distribution of brightness across the sky would change. Some regions that once glowed brighter due to lensing would fade. Others would lose their subtle distortions. From an observational standpoint, astronomy becomes more honest but less deep. This trade-off reflects a recurring theme in nature. Complexity provides information, but it also obscures. Dark matter made the universe harder to read at a glance, but richer in hidden signals. Remove it, and the surface becomes smoother, but the depth diminishes. There's also a philosophical layer here. Much of what we know about the universe comes from indirect effects. We learn by watching how light behaves under influence. When that influence disappears, so does a major source of insight. The universe grows quieter, not just physically, but epistemologically. It tells fewer stories through distortion. Even the night sky from within a galaxy would subtly change. The Milky Way's light, no longer subtly shaped by its own dark matter halo, would appear slightly different in brightness and distribution. The grand arcs of background galaxies seen through clusters would be absent. The sky would feel flatter, more literal. Yet this simplicity is not emptiness. Light still travels faithfully. Photons still cross space carrying energy, color, and time. Stars still shine, galaxies still glow. But light would no longer trace the invisible architecture that once guided it. There is something quietly poetic about this. Dark matter never spoke directly. It revealed itself by bending what already existed. Remove it, and the universe speaks more plainly, but with fewer metaphors. This also affects how the universe records its own history. Gravitational lensing acts like a fingerprint left by mass across time. It preserves evidence of where matter gathered, how structures evolved, how gravity shaped space. Without dark matter, future observers would have fewer records to interpret. The universe would be easier to see, but harder to understand in retrospect. And yet, the universe would not mourn this loss. Physics does not prefer mystery or clarity. It simply follows its rules. If space-time becomes smoother, light adapts. It travels on. As you lie here now, consider how often understanding comes not from what is clear, but from what is bent, delayed, or distorted. Shadows reveal shape, echoes reveal distance, lensing reveals mass. Remove distortion, and some truths become harder to uncover. Still, there is peace in simplicity. A universe with straighter light paths would feel calmer, less restless. Space would be less contoured, more open. The cosmos would appear more serene, even if it is less revealing. As this chapter comes to rest, one gentle question remains. If much of what we know comes from the way light bends around the unseen, what truths might be lost or gained when the universe grows easier to see, but quieter in what it chooses to show? Part 11. Could life exist without dark matter? Life depends on long-lived stars, stable galaxies, and heavy elements forged in stellar cores. Dark matter indirectly supports all of these by stabilizing cosmic environments. In a universe without it, stars would be rarer, galaxies less stable, and the conditions for life far more fragile. Life might still exist, but it would be far less common, scattered thinly across an emptier cosmos. To explore this question, it helps to slow down and trace the chain of conditions life requires, step by careful step. Life does not arise from complexity alone. It emerges from stability sustained over immense spans of time. Stars must burn steadily for billions of years. Galaxies must hold together long enough for multiple generations of stars to live and die. Elements heavier than hydrogen and helium must be created, dispersed, and gathered again into new systems. Each link in this chain depends quietly on gravity behaving in a very particular way. Dark matter does not create life. It does not seed biology or shape DNA. What it does is provide the cosmic patience that life needs. Long-lived stars are the first requirement. Stars like the sun burn slowly, offering a stable energy source over billions of years. In a universe without dark matter, such stars can still exist, but they are harder to come by. With weaker large-scale gravity, fewer dense regions form where gas can collapse efficiently. Star formation becomes sporadic and inefficient. The universe produces fewer stars overall, and fewer of them are born in the calm, long-lasting configurations that planetary systems prefer. The second requirement is stability, galactic stability. Planets need time, life needs consistency. Sudden changes in radiation, frequent stellar encounters, or chaotic galactic environments make complex chemistry difficult to sustain. Dark matter halos help keep galaxies coherent, preventing them from tearing themselves apart or dissolving too quickly. Without that invisible support, galaxies become transient structures, thinning and dispersing long before life has much time to explore complexity. Even if planets form around isolated stars, those systems are more vulnerable. In a thinning universe, stars drift farther apart, which can be protective in one sense, fewer close encounters, but it also means fewer opportunities for material exchange. The slow circulation of elements through generations of stars becomes less efficient. The chemical richness of the cosmos develops more slowly. Heavy elements are the third requirement. Carbon, oxygen, nitrogen, iron. These are not primordial. They are forged in the hearts of stars and scattered through space by supernovae and stellar winds. A universe with fewer stars has fewer of these enrichment events. Each generation of stars builds on the ashes of the last. When star formation slows, so does chemical evolution. This has cascading consequences. Fewer heavy elements mean fewer rocky planets. Fewer rocky planets mean fewer surfaces, fewer oceans, fewer places where complex chemistry can unfold. Life may still find a way, but its opportunities shrink. There is also the matter of time. Dark matter allows structures to persist for billions of years, creating long, uninterrupted stretches where conditions remain favorable. Without it, cosmic environments change more quickly on large scales. Galaxies disperse, star-forming regions fade, the window for life narrows. And yet, the universe is resilient. Life might still arise in isolated pockets. A single, stable star, born in just the right place, could host planets with the right chemistry. Biology does not require a crowded universe. It requires balance. In rare cases, that balance might still be achieved, but such cases would be exceptional. In a dark matter-free universe, life becomes a statistical rarity rather than a widespread possibility. Instead of billions of galaxies each hosting billions of stars, you have fewer galaxies, fewer stars, and fewer stable systems overall. Life becomes something that happens occasionally, quietly, in corners of the cosmos that briefly align with the right conditions. This scarcity has a subtle emotional tone. It does not imply failure. It suggests preciousness. Life in such a universe would be more isolated, more fragile, and perhaps more ephemeral. Civilizations, if they arose at all, would look out at emptier skies, seeing fewer stars, fewer neighboring systems, fewer hints of a larger cosmic community. The sense of vastness would remain, but the sense of connection would be diminished. And yet, even this quieter universe would not be hostile to life, just indifferent. Physics does not favor abundance or scarcity. It responds to initial conditions and available structures. Dark matter happened to provide a framework that made complexity easier to sustain. Without it, complexity is not forbidden. It is simply less likely. This perspective reframes the question in a gentle way. Life does not depend on dark matter directly. It depends on time, stability, and opportunity. Dark matter extends those opportunities across the cosmos. It gives life more chances to begin, to evolve, to persist. As you breathe now, consider how much of existence rests on indirect support. The things that matter most often rely on systems beneath them, systems that never announce themselves, never demand attention. Dark matter is one of those systems. It does not create life, but it makes room for it. There is also a humbling implication here. If life is rarer without dark matter, then the universe we inhabit is not just vast, it is generous. It is structured in a way that allows complexity to flourish repeatedly, not just once. The conditions that led to life on Earth may be uncommon in principle, but they are not isolated accidents. They are part of a larger pattern supported by invisible mass. In a universe without dark matter, that pattern thins, and yet life, wherever it appears, would still experience wonder. A sky with fewer stars is still a sky. A planet with one sun is still warmed. Consciousness, if it arises, would still ask questions, still seek meaning, still gaze outward. Perhaps that is the quiet reassurance. Even when the universe offers fewer chances, it never offers none. As this chapter gently closes, one final thought lingers. If life can persist even when the cosmos grows emptier and less forgiving, what does that say about the quiet determination of complexity and about the rare, delicate conditions that allow it to awaken at all? Part 12. Would the night sky look different? Over immense spans of time, yes. As galaxies disperse and stars escape their gravitational homes, the night sky would slowly dim. Fewer stars would remain bound together. Fewer galaxies would shine in the distance. The universe would not go dark, but it would grow quieter, lonelier, and less crowded with light. To understand how the sky would change, it helps to remember that what you see at night is not a snapshot of space, but a layered history of light. Every star is a nearby neighbor. Every faint smudge of a galaxy is a message sent millions or billions of years ago. The night sky feels full, because the universe has spent a very long time building structure and holding it together. Without dark matter, that fullness slowly thins. At first, nothing seems different. For millions of years, the constellations barely change. Stars continue their patient motions, tracing familiar patterns. The Milky Way still stretches across the sky as a pale river of light. From a human perspective, the heavens appear eternal. But on longer timescales, the changes begin to accumulate. As stars drift out of their galaxies, the dense bands of light begin to soften. The Milky Way grows narrower, less intense. Its brightest regions fade as stars spread out into wider orbits or leave the galactic disk entirely. What was once a glowing arch becomes a faint haze, then a suggestion rather than a presence. The most distant galaxies are affected first. As galaxy clusters dissolve and expansion carries systems farther apart, their light grows weaker. Some galaxies recede beyond the reach of visibility, not because they stop shining, but because space stretches too much between you and them. Their light becomes too faint, too redshifted to detect. One by one, the deep background lights wink out, not abruptly, but gently, as though the universe is dimming its lamps. This does not happen evenly. The brightest nearby stars remain prominent for a very long time. Planets still reflect starlight. The moon still glows. The sky is never empty. But the richness fades. The sense of depth diminishes. In today's sky, even in darkness, you are surrounded by layers, near stars, distant stars, galaxies far beyond the Milky Way. In a universe without dark matter, those layers flatten. The sky becomes shallower. There is less to see, and what remains feels farther away. Over billions of years, entire categories of night sky objects become rare. Globular clusters dissolve. Stellar streams stretch thin and fade. The dramatic silhouettes of spiral galaxies become harder to find. Elliptical glows soften into diffuse smears. Eventually, from most vantage points, the sky would be dominated by a single star, the local sun, and a sparse scattering of others. The idea of a sky crowded with light becomes a memory. Yet this dimming is not tragic. It is peaceful. There is something calming about a quieter sky. Without the visual noise of countless distant lights, the remaining stars feel more intimate. Each one stands alone, unchallenged by competition. The night becomes simpler, more meditative. In such a universe, darkness is not the absence of light, but the presence of space. The sky would also feel larger. When fewer objects anchor your gaze, the distances between them feel more profound. The black between stars becomes more noticeable, more expressive. Space asserts itself as a presence rather than a backdrop. This shift changes not just what you see, but how you feel beneath it. For ancient humans, the crowded sky inspired myths, calendars, and navigation. In a quieter universe, the sky might inspire contemplation rather than storytelling. Fewer patterns, fewer guides, more silence. Civilizations, if they existed, would grow up under skies that feel emptier. Their sense of the universe would be shaped not by abundance, but by rarity. Each star might carry more meaning simply because there are fewer of them. Even time feels different under such a sky. Without frequent cosmic events, no bright supernovae in nearby galaxies, no dramatic mergers lighting up the heavens, the passage of eras becomes less punctuated. The universe ages quietly, without spectacle, and yet the stars that remain continue shining for unimaginably long spans of time. Red dwarf stars, faint but enduring, dominate this future sky. They burn steadily for trillions of years, offering a gentle, persistent glow long after brighter stars have come and gone. So the sky never truly goes dark. It becomes subtle. The transformation of the night sky is not a single event, but a long fade, a slow turning down of brightness, a gradual increase in spacing. It mirrors the broader evolution of the universe itself, from dense and energetic to expansive and calm. As you lie here now, it may be comforting to realize that darkness in the cosmos is not emptiness. It is room. It is possibility. Even when fewer lights remain, the universe is still present, still vast, still unfolding. There is also a quiet lesson in this imagined future. We often equate richness with quantity, with how much there is to see. But meaning does not always scale with number. A single star in a vast sky can feel just as profound as 1,000 in a crowded one. In a universe without dark matter, the sky teaches patience. It teaches attention. Each point of light becomes something to linger on, not rush past. And perhaps that is the final comfort of this vision. Even as the cosmos grows lonelier and less crowded with light, it does not lose its capacity to inspire stillness. The night sky remains a place where time slows, where perspective deepens, where silence feels expansive rather than empty. As this chapter gently settles, one last question drifts into the quiet. When the universe offers fewer lights to look at, do we learn to see them more clearly, and in that stillness, to notice the vast, breathing darkness that was always there between them? Part 13. Is dark matter truly permanent? We don't yet know what dark matter is made of, only how it behaves. It may be composed of undiscovered particles, relics from the early universe, or something even stranger. Most models suggest it is stable over trillions of years, but physics allows the possibility that dark matter could decay, transform, or interact in ways we do not yet understand. Its permanence is assumed, but not proven. This uncertainty places dark matter in a rare category. It is essential, influential, and pervasive, yet fundamentally mysterious. We have mapped its gravitational footprint across the universe, traced its role in shaping galaxies, and relied on it to explain cosmic structure. And still, we do not know its true nature. We do not know whether it is eternal or merely long-lived. In physics, permanence is never guaranteed. Even protons, once thought immortal, are now suspected, by some theories, to decay over unimaginable spans of time. Stability, in nature, is often a matter of scale rather than absolutes. Dark matter may feel permanent because it endures far longer than anything human experience can touch, but that does not mean it lasts forever. Many leading models describe dark matter as a new kind of particle, weakly interacting and massive. These hypothetical particles would have formed in the earliest moments after the universe began, freezing out as space expanded and cooled. In such models, dark matter is stable by design, protected by symmetries that prevent it from decaying. But symmetry in physics is a delicate thing. We have learned repeatedly that symmetries can break. Forces once unified can separate. Particles once thought fundamental can reveal hidden structure. If dark matter's stability relies on a symmetry we do not yet understand, then its permanence may be conditional rather than absolute. There are also models in which dark matter is not entirely inert. It may interact with itself in subtle ways, slowly transforming over time. It may decay into lighter particles, so weakly interacting that we have not yet detected them. It may even change form as the universe evolves, leaving behind a different cosmic signature than the one we observe today. If such decay exists, it would be extraordinarily slow. Slow enough that galaxies have had billions of years to form and mature. Slow enough that the universe we see today still bears dark matter's unmistakable imprint. But slow does not mean never. In this sense, dark matter's story may not be finished. There is something quietly profound about this possibility. Dark matter is often spoken of as a static background, an invisible framework that simply exists. But if it can change, decay, or fade, then it is not just scaffolding. It is a participant in cosmic evolution with a life cycle of its own. This idea reshapes how we think about cosmic time. The universe may not be built on eternal components, but on long-lived phases. Dark matter may be one such phase, a dominant presence for trillions of years, eventually giving way to something else. If that were true, the universe would not be broken by its loss. It would transition. And transitions in nature are rarely abrupt. Even now, scientists search for signs of dark matter instability. They look for faint excesses of radiation, unexplained particles, subtle deviations in cosmic behavior. So far, the silence continues. Dark matter behaves as though it is stable, patient, and enduring. But silence is not certainty. It is worth remembering that much of physics advances not by direct observation, but by patience. The universe often reveals its deepest truths only when observed across enormous spans of time. Dark matter may be speaking very slowly. There is also a humbling lesson here about knowledge itself. We often build our understanding on assumptions that feel solid, only to discover later that they were provisional. Dark matter's permanence feels intuitive because it has shaped everything we see. But intuition is not proof. The universe has surprised us before. At one time, space was thought to be static and eternal. Then, expansion was discovered. At one time, the cosmos was thought to be filled only with visible matter. Then, dark matter emerged. At one time, gravity alone was thought to govern cosmic fate. Then, dark energy revealed itself. Each discovery arrived quietly, reshaping everything without spectacle. Dark matter's possible impermanence fits this pattern. If it is not permanent, then the universe we inhabit is part of a temporary arrangement, one that allows structure, life, and complexity to flourish for a long time, but not forever. This does not diminish its beauty, it deepens it. There is a strange comfort in knowing that even the most foundational elements of reality may be transient. It reminds us that change is not a failure of the universe, but its method. Stability exists to allow complexity to arise. Once that purpose is served, transformation follows. As you rest here now, consider how much of your own experience relies on assumptions of permanence. The ground feels solid, the sky feels fixed, the stars feel eternal. And yet, everything is moving, changing, aging. Dark matter may be no different. If it endures forever, then it will continue to quietly support the universe's structure long after all familiar stars have burned out. If it fades, then the universe will slowly loosen, expanding into a calmer, more minimal state. Either outcome is consistent with the laws of physics as we understand them. What remains constant is not matter, but process. The universe is not built from things alone. It is built from relationships, between mass and motion, between space and time, between stability and change. Dark matter is one of those relationships made manifest. Whether it is eternal or temporary, its role has already been profound. And perhaps that is the most important realization. Permanence is not required for meaning. Dark matter does not need to last forever to matter. It only needs to last long enough to shape a universe capable of asking questions about itself. As this chapter settles into quiet reflection, one final thought drifts gently forward. If even the unseen foundations of the cosmos may one day change or fade, what does that tell us about the beauty of a universe defined not by what lasts forever, but by what endures long enough to give rise to wonder? Part 14. What does dark matter teach us about reality? Dark matter reminds us that the universe is not defined only by what we can see. Most of reality operates beyond direct perception, governed by laws revealed through motion, pattern, and inference. The stars you see are only a small fraction of what exists. The rest is hidden, shaping outcomes without ever announcing itself. This realization quietly reshapes how we understand truth itself. For most of human history, knowledge was tied to sight, sound, and touch. What could not be sensed directly was often treated with suspicion or dismissed entirely. And yet, the deeper science has looked, the more it is found that the most influential parts of reality rarely reveal themselves to our senses at all. Dark matter is one of the clearest expressions of this idea. It does not glow. It does not leave footprints. It does not announce its presence with color or heat, and yet it outweighs everything you can see. It guides the motion of galaxies, bends the paths of light, and shapes the large-scale architecture of the universe. It is real not because we perceive it directly, but because the universe behaves as though it must be there. In this way, dark matter teaches us that reality is often inferred, not observed. We know the wind exists not because we can see it, but because leaves move and pressure changes. We know gravity exists not because we can touch it, but because objects fall and planets orbit. Dark matter belongs to this same category of truths, known through consequence rather than appearance. This has a humbling effect. It reminds us that the universe is under no obligation to present itself in forms that are intuitive or comforting. Much of what matters most happens quietly, beyond perception, expressed only through long-term patterns and gentle influence. Dark matter also teaches patience. Its effects are not immediate. You cannot point to a single star and say, "That is dark matter at work." Instead, you must look across millions of stars, across entire galaxies, across billions of years. Only then does the pattern emerge. Only then does the hidden presence reveal itself. This is how much of deep truth works. Reality often speaks softly over long durations. It leaves clues rather than declarations. It requires careful listening, comparison, and restraint. Dark matter did not announce itself with a single experiment. It emerged gradually as evidence accumulated and alternatives failed to explain what was seen. There is also a lesson here about humility and knowledge. Even now, we do not know what dark matter is. We know what it does, how it behaves, and where it must be. But its nature remains unknown. This is not a failure of science. It is a reminder of scale. The universe is vast beyond comprehension, both in size and in depth. That we can infer the existence of something we cannot yet identify is not a weakness. It is a quiet triumph of human reasoning. Dark matter also reframes how we think about dominance and visibility. In human experience, the loudest, brightest, and most visible things tend to feel most important. In the cosmos, the opposite is often true. The things that shine are not the things that weigh the most. The things that draw attention are not the things that hold everything together. The visible universe, stars, planets, glowing gas, turns out to be a thin frosting on a much deeper structure. What we see is not the foundation, it is the decoration. This realization invites reflection beyond physics. It suggests that influence does not require visibility, that stability often comes from unseen support, that outcomes are shaped by forces operating quietly in the background. Dark matter teaches us that absence of evidence is not evidence of absence. It teaches us to be cautious about declaring something unreal simply because it does not announce itself in familiar ways. It also teaches us something about perspective. From within a galaxy, dark matter is imperceptible. From within a solar system, it is irrelevant. From within a human lifetime, it is static. Only when we step back far enough, spatially and temporally, does its importance become clear. This pattern repeats across knowledge. Many truths only reveal themselves when viewed from the right distance. There is a gentle poetry to this. The universe contains far more than it shows. It carries layers beneath layers, structures beneath appearances. Dark matter is not an exception, it is an example. And this example changes how we relate to mystery. Instead of seeing the unknown as a void, dark matter shows us the unknown as something active, structured, and meaningful, even before it is understood. Mystery, in this sense, is not ignorance. It is unfinished knowledge. Dark matter also reminds us that our senses evolved for survival, not for cosmic accuracy. Human perception is tuned to a narrow slice of reality, pressures, temperatures, wavelengths, useful for living on a planet. The universe operates far beyond those scales. Expecting it to be fully visible to us would be the greater illusion. Science becomes, in this light, an extension of perception. Instruments replace eyes, mathematics replaces intuition, patterns replace appearances. Dark matter sits at the intersection of all three. There is also something quietly reassuring here. Even though most of reality is hidden, it is not chaotic. It follows rules, it behaves consistently. The unseen is not arbitrary, it is lawful. Dark matter does not flicker in and out of existence. It does not behave unpredictably. It does its work steadily, reliably, over billions of years. The hidden parts of the universe are not wild, they are disciplined. This challenges a common fear, that what we cannot see must be dangerous or unknowable. Dark matter shows the opposite. The unseen can be stabilizing, it can be supportive, it can be the reason things hold together at all. As you rest now, consider how often this applies beyond the cosmos. How many systems rely on unseen structure? How many outcomes depend on quiet processes rather than visible actions? How many supports go unnoticed simply because they are consistent? Dark matter teaches us to value inference, to trust patterns, and to accept that understanding often comes before explanation. It also teaches us that wonder does not require spectacle. There is awe in quiet influence. There is beauty in what never asks to be seen. And perhaps most importantly, dark matter teaches us that reality is deeper than appearance, but not inaccessible. Even when we cannot touch or see something, we can still know it through care, patience, and attention. As this chapter gently settles, one final reflection remains. If the majority of the universe exists beyond direct perception, shaping everything without revealing itself, then perhaps the truest way to understand reality is not by looking harder, but by learning how to listen to what motion, balance, and pattern are quietly telling us. Part 15. Why does an invisible universe matter to you? Even as you rest here, the utairi structure of your existence is supported by forces you will never feel. Dark matter is one of them, quiet, ancient, and vast. Its presence teaches humility, reminding us that reality is deeper than appearance, and that stability often comes from what remains unseen. And as this quiet journey continues, one gentle question lingers in the dark. What else is shaping your world without ever asking to be noticed? To begin answering that question, it helps to gently shift perspective from the scale of galaxies back to the scale of a single human life. You are small in the universe, but you are not separate from it. Every atom in your body was shaped by cosmic history. Every stable orbit, every long-lived star, every calm night sky that ever allowed life to develop was made possible by forces that worked patiently, invisibly, long before you existed. Dark matter matters to you not because it touches you, but because it made your world possible without ever demanding credit. It is easy to assume that what affects you must be close, loud, or immediate, but much of what sustains life operates at a distance, both in space and in time. Gravity from the sun keeps Earth warm and stable. Nuclear reactions deep in stellar cores forge the elements in your bones. And dark matter, spread across the galaxy, helped ensure that stars like the Sun could exist in stable environments for billions of years. These influences are not dramatic, they are dependable. Dark matter did not shape your day, but it shaped the universe that shaped your day. It did not guide your choices, but it guided the galaxies that allowed choices to arise at all. It exists far outside your awareness, yet it quietly participated in the long chain of conditions that led to your presence here now. This realization carries a subtle emotional weight. It reminds us that meaning does not require visibility, that importance does not require attention, that some of the most essential contributions are made silently, without recognition. There is a quiet dignity in that. In a culture that often celebrates what is seen, heard, and acknowledged, dark matter offers a different model of significance. It contributes without display. It supports without asserting itself. It shapes outcomes without ever appearing in the final picture. And this mirrors something deeply human. Much of what sustains your own life is invisible. The steady work of your heart, the silent chemistry of your cells, the long, unnoticed habits that keep systems running smoothly. You do not feel these processes moment by moment, but if they stopped, everything would change. Dark matter teaches us that invisibility does not equal insignificance. It also invites humility. The universe you inhabit is not designed around human perception. It does not prioritize what you can see or feel. Most of its mass, most of its influence, exists outside your sensory world. And yet, you are still able to understand it, not through intuition, but through patience, inference, and care. This tells us something hopeful about knowledge. Even when reality is hidden, it is not closed. Understanding is possible, but it requires listening to patterns rather than appearances. Dark matter matters to you because it reminds you that you are part of something much larger than yourself, something that does not revolve around your perspective, yet still includes you. It places your life within a vast ancient context where outcomes unfold over billions of years and countless quiet interactions. There is comfort in this scale. Your worries, your thoughts, your fleeting moments exist within a universe that has learned how to hold itself together, quietly, without urgency. The same patience that allowed galaxies to form also allows you to rest here now, supported by a world that does not require your constant attention to continue. Dark matter also reframes how we think about control. The universe is not held together by forceful intervention, but by balance, by relationships between mass and motion, by structures that emerge naturally when conditions allow. Nothing is being actively managed, and yet everything works. This can be deeply calming. It suggests that stability does not always require effort, that sometimes things hold together simply because the conditions are right. As you lie here, breathing slowly, consider how many unseen systems are working on your behalf. The atmosphere regulating temperature, the planet's gravity holding oceans in place, the galaxy's history providing a calm stellar neighborhood. None of these require your participation. They simply are. Dark matter belongs to this category of quiet guardianship. It also offers perspective on uncertainty. We do not yet know what dark matter is, and yet we trust its effects enough to build our understanding of the universe around it. This teaches us that it is possible to live with incomplete knowledge without fear. You do not need full understanding to find stability. There is also something profoundly grounding about knowing that reality is deeper than what appears. It frees you from the pressure of surface-level explanations. It allows mystery to coexist with confidence. The universe can be unknown and still reliable. Dark matter has been doing its work for billions of years without asking to be noticed. It does not rush. It does not fluctuate wildly. It does not demand answers. It simply continues, shaping outcomes with extraordinary patience. And in that patience, there is a lesson. You do not need to see every influence in your life to be supported by it. You do not need to understand every force to trust that things can hold together. The unseen does not have to be threatening. It can be steady. As this journey through invisible structure comes to rest, let the final question settle gently, without needing an answer. What else might be shaping your world right now, quietly, invisibly, patiently, holding things together? While you rest, you do not need to find it. You do not need to name it. It is enough to know that the universe has always been built this way, supported by what is unseen, sustained by what does not ask for attention, moving forward calmly, whether or not anyone is watching. And in that knowledge, you are safe to let go, to drift, and to rest beneath a universe that knows how to hold itself together, quietly, endlessly, and without ever needing to be seen. As this quiet journey comes to rest, it helps to remember where we've traveled, through invisible matter and silent gravity, through galaxies held together by what cannot be seen, through a universe that does not announce its foundations, yet depends on them entirely. Dark matter never revealed its face, and yet it shaped everything. It taught us that stability does not always come from what shines. That meaning does not always arrive loudly. That the deepest structures of reality often work patiently, far beyond our awareness. And perhaps that is the most comforting truth of all. As you lie here now, breathing slowly, the universe continues its gentle work. Stars burn steadily. Space stretches calmly. Unseen forces hold patterns together without effort or urgency. Nothing needs your attention. Nothing asks you to solve it. Everything is allowed to continue exactly as it is. If there is peace to be found in science, it lives here, in the realization that the universe does not rush, does not panic, and does not require constant control to remain whole. It simply balances, it endures, it unfolds. Thank you for sharing this quiet moment with me, for listening, for wondering, for resting beneath a cosmos that knows how to carry itself. And now, with nothing left to figure out, nowhere left to travel, you can let the darkness soften around you and drift gently into sleep.